In Unit 3, we continue the analysis of graphing, but up until Unit 1, through Unit 1 and 2, we've concentrated on quadratics, exponential growth, linear, and absolute values. Well, we're just moving on in Unit 3 to higher order polynomial functions or equations. Now in Objective 1 is simply an exploration objective. We're going to use the help of the graphing calculator, which most of you guys are real familiar with, Desmos.com. And if you put in this equation, this is a sketch of the graph you get out. We're going to explore some of the characteristics of this graph. The first one is, what's the highest degree of this polynomial equation? It's x to the fourth. So what's the entire term? It's 3x to the fourth power. Now, it's that highest degree term that's going to dictate a lot of the characteristics of the graph. So, is the leading coefficient of that term positive or negative? Well, it's a positive 3, so it's positive. Is the degree of the exponent even or odd? It's obviously even. Now, there are characteristics when you have this situation. This graph is referred to as a high to high behavior graph. It starts high, it does some bouncing around, but it ends going up also. So that's called high to high. Moving on to the next one. When you put in this equation, this is a sketch of the graph that you get out. And again, all we care about is the highest degree term, which happens to be 2x to the fifth. Most of the time it'll be the first term, but don't get caught. It doesn't have to be. They could put things out of order and put the highest degree term anywhere. So the highest degree term is 2x to the fifth. Is the leading coefficient positive or negative? Again, it's positive. Is the power itself, the exponent, even or odd? It's odd. And the behavior that we call this graph is it starts low. We're just going left to right. It starts low, but it ends high. So it's a low to high graph. Now, looking at the next one. Another polynomial equation. Negative 2x to the fourth is the highest degree term. The coefficient is negative, but the power, the exponent, is even. And notice its behavior. It starts low, it does some bouncing around, but it also ends low. So this is called low to low. And then the last one on this page, here's the graph. Negative x to the third power plus 2x squared plus 5x minus 1. Again, a four-term polynomial. The highest degree term is negative x cubed, which means the leading coefficient is negative 1, so it's negative, but the exponent is an odd exponent. So its behavior is it starts high, but it ends low. So we call that high to low. Now, Desmos will tell you these important points that I've marked, But right now on objective 1, we're really not concerned of where those points are. What we're concerned about more than anything else is just a sketch of the graph and how the graph behaves. The 4 examples that I just did can be summed up in this chart right here. When the highest power is an even power, and the leading coefficient was a positive number, the end behavior of the graph was high to high. That's what it did. When it was an even power, when the highest power was even, but it was a negative coefficient, if you go back and look, the graph went from low to low. When the highest power was odd and it was a positive coefficient, it went from low to high. And when the highest power was odd and the leading coefficient of that term was negative, it went high to low. So for the following function, y equals negative x to the 5th power plus 2x cubed minus 8x squared plus 9. Without graphing, we can figure out some things that the characteristics of the graph. So the highest degree would be, this would be a 5th degree function because the highest power is 5, which is an odd number. Now the leading coefficient of that term was negative 1, which is obviously negative. So what would this graph do if we actually graphed it? The end behavior would be odd degree negative coefficient. Odd degree negative coefficient, it would do this. It would start high and it would end low. So it would go from high to low. Start high, end low. Okay, let's explore the behavior of the next equation. It's a 4-term equation, but everything pretty much depends on this first term, the highest term, not necessarily the first one, but in this one it is, which is 4x cubed. So 4x cubed, that's what we need to explore a little bit. The degree of the exponent is odd because it's a 3. And the leading coefficient is positive because it's a 4. So those are the characteristics that are going to help us determine what it does. Odd, positive. Well, our chart tells us odd, positive has a low to high behavior. Low to high. So it should start low and it should end high. Now, if you go to a graphing calculator or Desmos, you'll find that that's exactly what it does. Your graphing calculator will tell you that it does something pretty close to this. It starts here, it makes a turn right here, but it then makes another turn right there, and it does something like that. And sure enough, that is a low to high graph. For the last part of the video, we're going to take a look at 3 different graphs. We don't know the equation that made the graph, but we do want to figure out some characteristics of that equation. And along the lines, we're going to answer these 4 questions. So, graph number 1. We know it goes from low to high. Well, that's what question A asks. Describe the end behavior. Low to high. Now, I've recreated the chart that's at the top of the notes right here. so we don't have to keep bouncing back up. Is it an even or an odd degree function? Well, if it goes from low to high, it has to be an odd function, meaning the term with the highest exponent, the exponent itself has to be an odd exponent. Now, as long as we're there, let's skip to the D question. Would the leading coefficient of that term be positive or negative? Well, if it goes from low to high, the leading coefficient must be positive. And now we'll go back up to the C question. State the number of real zeros or x-intercepts. How many times does this graph either touch or cross through the x-axis? 1, 2, 3. Okay, graph number 2. How do we describe it? High to high. Now the next thing, what makes a function a high-to-high function? Well, the highest exponent has to be an even exponent, and the leading coefficient of that particular term has to be positive. And then the C question asks, how many times does this graph either touch or pass through the x-axis? And it's twice. So it has 2 real zeros or x-intercepts. All right, the last graph they show us, it definitely goes low to low. It starts low and it ends low. So what makes a graph a low to low graph? The power has to be an even power. When you identify the term that has the highest power, that power will be even. And the leading coefficient of that power will be negative. Now, the last question is, how many times does this touch the x-axis? How many x-intercepts or zeros? 1, 2, 3, 4. Now, a couple more questions that are asked on the worksheet would be something like this. On graph number 2, how could I eliminate all the x-intercepts? Well, if we just shifted the graph up, I don't know how many units it would take, but if we shifted the graph up a certain amount of units, we could get this lowest relative minimum right there to be above the x-axis, and it would no longer touch the x-axis. Now, for problem number 3, it works the other way. How could I eliminate the x-intercepts? I could shift the entire function down a certain number of units, and there would come a point where I don't have any of these peaks either touching or above the x-axis anymore. Now, if we go to graph number 1, how could I eliminate the x-intercepts? Well, the answer is I can't, because if I shifted up, yeah, I could get to a point where this is above the x-axis, but I could never get to a point where this never passes through the x-axis. And then it'd be the other way if I went down. If I went down, if I shifted down, I could get to a point where this would be below the x-axis, but it would never eliminate the cross right there. So sometimes you can eliminate the x-intercepts if you want, sometimes you can't. So it takes either a shift up or a shift down. And as we learned in the previous units, if you want to shift up or down, you just simply add or subtract at the end of the equation.